Good afternoon, everyone. It's my great honor to be here in memory of Fred, who has been a great mentor to me. But Paul has given me a sort of impossible task to talk about cosmology in general. So I'll try my best to give you a sort of partial view, mostly focusing on the observational side. And even though Fred did not work directly in the fields that I'm going to talk about, he has nevertheless been very instrumental and influential in these areas, which I hope to convey to you. Just very briefly, the timeline of the history of the universe in our now very successful Big Bang cosmology. So at the very beginning of the universe, the universe underwent a very fast expansion. Now it's in the right after the Big Bang. And now the favorite model is called inflation, and is a topic of really under a very hot topic under lots of investigation right now. So the universe expanded and cooled down to allow neutrinos to decouple from the hot plasma, and then the protons and electrons were able to recombine and let out the cosmic microwave background radiation that we see today. And the initial fluctuations seeded by the mechanism in the early universe that we don't quite understand yet were able to grow via gravitational instability that gradually form dark matter halos, and then baryons, attracting baryons. And when baryons were able to cool down via mainly the H2 cooling, then we had the formation of the first stars, first galaxies, or first quasars that let out the UV radiations that reionized the universe at about 500, when the universe was about 500 million years old. And afterwards, there was a formation of galaxies and evolution of galaxies that evolved into the universe that we see today. And as we know now that the universe is now dominated by the dark energy today. And the ratio for recombination, however, the neutrino is actually a fairly important energy source at that time, which I'll briefly mention later. So, what are the major questions in cosmology now? So, as you know, as I just mentioned, that what created the initial perturbations at the very early universe, that we still don't know what source them and what their properties are. And of course, now we live in a dark energy dominated universe, and we actually know literally nothing about it today. So I guess the pillar of observational cosmology is to use basically the distribution of CMB photons to try to understand these questions, and also by using the distribution of galaxies at date times that traces the distribution of matter, trying to understand the growth of structure and the expansion of the universe. So, so two questions, basically hope to address very briefly in this talk is how do we probe inflation with CMB and large-scale structure, and also how do we tackle try to quantify the dark energy, and what's the community thinking about these days. And I will, of course, so there's actually a wide range of probes under this sort of big structure, and I will only very briefly talk about in the context of CMB polarization, and also large-scale structure probes in the context of non-Gaussian nonity tests. And I'll also mention the gravitational waves that actually CMB BMO is trying to measure from the primordial gravitational waves coming from the inflation. And also, I'll talk about the plans for using pulsar timing arrays trying to probe gravitational waves. So, okay, so very briefly, the CMB. So this is the CMB temperature and isotropy pulse spectra as of 2015. So this is the power in microkelvin squared as a function of multiple L or angular scales in reverse direction, so large scales, small scales. And as you know, so this the CMB pulse spectra has been mapped to really high accuracy by a combination of probes. Mostly, in this version is coming from Planck and ACT and the SPT experiments. So people basically wonder, how are we done with the CMB? Actually, on large scales, yes. So I guess from scales larger than about 0.1 degrees, we are basically cosmic variance dominated. So then, which means that we are basically limited by our observable universe. There's no more information to be learned from the CMB temperature pulse spectra. However, on small scales, there are still only a handful of measurements, and we can still, now the CMB temperature fluctuations are now focusing on the small scale measurements at the degree or actually unminute scales or smaller. And so as I think Shen mentioned that our cosmological model has been very well explained by 6 parameters. That basically fit beautifully the CMB temperature pulse spectra. And these parameters are the baryon content of the universe, the cold dark matter, and the size of the sun horizon, which basically gives us information about the geometry of the universe, and basically the amplitude and the shape of the initial fluctuations that I mentioned. And then there's a tau parameter, which is the absolute depth to Thomson scattering created by basically the realization due to the formation of the first galaxies. So let me just take a step back by 15 years. So this is now basically the standard cosmological model that we all think we understand. But actually, only 15 years ago, this is what the CMB pulse spectra looked like. So I think if you remember, in 1998, Boomerang just returned with the measurement of the first peak of the CMB at L of around 200 or so. So that was basically the foundation, or the first epic moment that we understood that, well, we thought that we lived in a flat universe. And at that time, people weren't even sure whether there were this baryon acoustic oscillation features in the CMB could be measured around 2000. And you can see that CMB is actually a very crowded and competitive field. There were many, many measurements, many different experiments going after this signal. So I just wanted to mention that in 2000, the AMIBA project was basically conceived trying to go after the CMB polarization signal. So what we are talking about here is just the main temperature, CMB main temperature signal. But AMIBA was designed to look for the secondary CMB signals, such as caused by the Sonia-Yezedovich effect, and that basically found the hot electrons in clusters, and also it was meant to go after the CMB polarization signals. So this, we were able to find this meeting in 2001. I think that, well, I guess AMIBA was conceived. Oh, sorry, I think. Sorry, I meant to say this. This is the first publication about AMIBA that I was able to find that was championed by Fred in 2000. That was basically for a meeting in AS that I think that was to introduce the AMIBA experiment to the international world. And in 2001, there was an international meeting with all the major CMB players in the field. As you can see from Lyman Page, John Costrom, in the science community, also with Chongpei and Howard here. And basically the meeting, I was going to say that the AMIBA was really a very daring and ambitious experiment that I think Fred was really the driving force of it. And here are just some pictures of from the proceeding. I think Fred was standing here. And this was in collaboration with National Taiwan University, and the meeting, I think the meeting was half time in NTU and half time in Guangdian. But anyway, so AMIBA was in operation, as several of the speakers are mentioning, was operation in 2007, and expanded in 2009, and now it's actually still active and being upgraded for doing having a new digital backend, a spectral backend. And so back to the sort of CMB history side, that the CMB BMO polarization was actually detected in year 2002 by the DESI experiments. So you can see a sort of close similarity in design for amoeba and DESI in 2002. So the EMO polarization is basically a component of the polarization component that is curl-free component. And then the BMO polarization that you heard about a few years ago was first detected in 2014. Basically, this is the divergence-free component of the CMB polarization that is basically could be a signature coming from the inflation. And then, as you know, the interpretation of this CMB BMO was actually controversial. But however, it is the detection itself is solid, I think. Just the interpretation of whether this is coming from inflationary or whether this was just a condemnation, it was a debate. But I think there were basically I think we haven't seen the smoking gun of inflation. Basically, was the BMO inflationary polarization signal yet. So putting things in context, so this is again the pulse spectra as a function of multiple L. And the pulse spectra is still in units of microkelvin square. And this was the temperature pulse spectra that I talked about earlier. And you can see that this is the EMO polarization pulse spectra. This is the BMO polarization pulse spectra. So notice that there's a huge span in amplitude here in magnitude here. So I think the CMB field has been very impressive in pressing down in sensitivity and measurement just over about 10, 15 years down to this level. And I think right now the field is going on the large scale BMO measurement, trying to measure this CMB, the inflationary signature, the parameters called R, which is the tensor to scalar parameter that tells you that gives you an idea of the energy level of inflation. And also on small scales, the field is going for measuring the temperature, small scale fluctuations, and also the BMO fluctuations, and also the lensing of the CMB due to the large scale structure on small scales that give us more information about the neutrino properties. One could use this to measure the sum of neutrinos and the basic neutrino density, basic neutrino density here. So the plan for the the field of CMB is to, now if you probably have heard, it's called the CMB S4, which is gather all the community together, trying to push down the limits for sensitivity. And we are basically in this area, in the language of the DOE, we are in the stage 3. Sorry, we are in the stage 3 experiment right now. So with the tech array or the Simon's array, that's basically people call stage 3.5, pushing down in sensitivity, and then eventually the company hopes to be put together and have a very large number of detectors in the year of 2020 or so. So CMB stage 4 is of order 100,000 detectors that will basically require the community to come together to push for this large-scale experiment. So in terms of parameter constraints, in stage 4, so the goal for CMB stage 4 is again to measure the neutrino properties and also to measure the the tensor to scalar parameters, and these are the constraints that the community now is pushing. And in combination with large-scale structures, there's also hoping to constrain the dark energy equational state. Okay, so moving quickly to gravitational waves. So I think one of the most exciting events that happened in my career was the detection of gravitational waves by LIGO in 2015 on September 14th. So this was the waveform detected by two different LIGO sites, and they actually match. And the interpretation was that this was produced by two stellar mass black holes. And so by looking at the waveform that's spent over the sub-seconds, that one could see the in spiral phase and the merger and the ring down phase that could predict it very well from post-Newtonian calculations and numerical relativities, basically predictions of GR. So this, I think, is really a remarkable event. To put this detection in context of what I just talked about CMB beam mode. So this is the spectra of a gravitational wave as a function of the strength or the amplitude of gravitational waves. So the LIGO detected basically a low frequency event that's caused by stellar mass mergers. And LISA, or the space version, will be able to look at the black hole masses with larger black hole masses mergers and binaries. And but this pulsar timing array that I want to talk about is we'll be able to look for the signature from supermassive black holes, binaries, and mergers. And of course, the CMB is probing lower frequencies on this spectra. So what is a pulsar timing array? So basically, instead of using laser interferometers as detectors, one could use millisecond pulsars as detectors on the sky, trying to measure the ripple of curvature, the ripple of gravitational waves passing by. So the idea is that these millisecond pulsars are very fast spinning, highly magnetized neutron stars, and their arrival time of the pulse arrival time can be measured to super high accuracy, and you can therefore use them the arrival time as a measure for the displacement of space and time. When there's a gravitational wave propagates through it, you can use the position or the arrival time of these multiple quasars measured to high precision to detect these tiny ripples in space-time. And the signature that the pulsar timing array are going after is called the stochastic background, which is basically the superposition of all the black hole, supermassive black hole binaries, the gravitational waves generated from these events. Or now people are starting to look at the continuous wave limit, which Chopin is involved in, where where you can be actually, if you have enough angular resolution, or if you have enough pulsars, you can actually detect a single event from the binary black hole orbiting. So one of the major pulsar timing array is called nanograph. Actually, one of the 3 international pulsar timing arrays, and nanograph is the one in North America. And actually, Fred played a major role in having it established. So nanograph actually, the collaboration actually awarded Fred. Sorry, we couldn't read very well. Actually, awarded Fred a recognition for his vision and mentorship to establish this collaboration in March 2016. And so again, this is the gravitational wave frequency and the amplitude. And you can see that this is the constraint now set up by nanograph in strain. And then these are the model predictions from all the structure formation, black holes, expected signal of gravitational waves. You can see that in the next coming 5 years, nanograph will be we putting pretty interesting constraints on all the scenarios of black hole merger in the universe, and or hopefully detecting the gravitational waves through from supermassive black holes. So I have actually a direct quote from one of the founding members of Nanograph. This is from Scott Ransom. He's a member at NIO, and he was basically saying how Fred was instrumental in pushing him and helping him establish Nanograph. And now the world of pulsar timing has actually come together with an array in Australia and an array in Europe, trying to form an international pulsar timing array collaboration, trying to go after this signature. So I think Fred's influence was really critical to make all this happen. So finally, switch back to logical structure. So as I tried to explain very quickly, that instead of using the distribution of CMB photons, we can use the distribution of galaxies as to trace the underlying dark matter in 3 dimensions or in 2D, and in turn calculate or measure its two-point correlation function, or two-point statistic in this case, trying to measure different signatures from the imprinted from the early universe. And in this case, we'll be trying to look for the imprint of the baryon acoustic oscillation effects on the distribution of matter, which is called the BAO. And this is basically the constraint is very complementary to the CMB constraints. So here is the basically the constraint on the geometry of the universe and the angular diameter distance and the expansion rate. And you can see that this is the constraint from the CMB, and this is the constraint from logical structure. And the size of error bar is still quite large from logical structure, but the point is that the angle, or they are actually complementary, and it will help basically narrow down the constraint very largely. So very quickly to flesh out that, so as I mentioned, at late times where we live in the dark energy dominated universe, so using logical structure actually provide a really good level arm to measure the dark energy, so which is will actually much better than what CMB can provide. And of course, you can help with CMB to constrain the tensor to scalar ratio and also to neutrinos. So another feature about logical structure, I think these days, is that we are going to sort of in a brute force way to measure to larger and larger scales with more and more independent modes. So one of the interesting parameters that logical structure can help is to measure the inflation. Again, now this is to measure the non-Gaussianality of the initial fluctuations, which basically provides an idea of how complex the inflation scenarios was, whether it was single field or multi-field, while the CMB is probing the energy level of inflation. And one can use basically the galaxy clustering on very large scales to do this. So I won't go into the details, but the idea is that the logical structure provides a different measurement from the CMB to probe inflation. And logical structure actually, because we are probing a 3-dimensional universe rather than the 2D slab of the CMB, there's actually more information eventually in the logical structure. So basically, this is the sort of logical structure stage 4 surveys that come up in around 2020. So these are the planned W1st satellite, and this is a planned Euclid, and also the LSST telescope. So basically going this way, the information content increases this way. So again, the idea is that we brute force trying to map as large as possible the size of the universe in order to get more information for all kind of for all the constraints that we talked about. And just to put some of the numbers. So as you can see, the basically the size of the universe or the cosmological volume that we are able to probe, the larger, the better, and also the more number of independent nodes or the more number of independent information, the better. So the CMB is basically at about 10 to the 6th number of nodes, and compared to all the logical structure that's coming online. So you can see that the Euclid satellite is basically approaching the information content of CMB that will be coming on in 2020. And with the last maybe 5 minutes or so, we're hoping to tell you that another approach for going after the large scale structure, rather than doing the typical galaxy redshift spectroscopy survey or imaging survey, is that we're hoping to use 21 centimeter intensity mapping as a tool to achieve that. So intensity mapping in a nutshell is that we do not try to measure individual sources or individual galaxies, but rather we measure the brightness temperature fluctuation of, in this case, 21 centimeter associated with larger structure in 3 dimensions. And therefore, we hope to access a very large volume very quickly and efficiently. So the eventual goal, or hopefully the potential, is that we'll be able to map a very significant fraction of the observable universe. So this is basically the schematic diagram shows the size of the observable universe where we're in the middle. And hopefully with 21 centimeter emission line from neutral hydrogen, we'll be able to reach a very high redshift ratio around 50 or so. So just a quick calculation shows that the up to ratio of 50 or so, there will be about 10 to the 15 modes available for with 21 centimeter line compared to the CMB, which at the 10 to the 6 modes. There's still a lot of information to be gained this way, or at least that's the idea. So we have started actually, so the people have been, this is a relatively new field, and people started to conceive and work on this around 2008 or so. And in 2010, we have published sort of first detection of 21 centimeter intensity mapping using a green band telescope, where we try to map the larger structure between redshift 0.6 and 1, and where this is a spatial dimension. And we were able to measure a phosphorylation signature with the distribution of galaxies traced by the D2 galaxy survey. And this is the basic phosphorylation measurement that we're able to do at the 4 sigma level, and measuring things at about 10 megapascal scales. And the amplitude of the phosphorylation gives an idea of the abundance of H1 at ratio around 0.8 or so. So I just wanted to highlight that Fred actually was the driving force behind this. After we made the initial measurement, Fred actually organized intensity mapping workshop in Charlottesville and gathered a lot of us, trying to push us to go after this signal in a larger way. And Fred actually helped us establish both the scientific program and also an instrumental part of the project called GPT-HIM, which he also named. So with GPT-HIM, we have been working on collecting more data, redshift H1 data from the GPT. We have about 800 hours at hand trying to measure the H1 autopulse spectra ratio on 0.8 by itself as the first step to use 21 centimeter as a probe for cosmology. And in parallel, we also have an instrumentation program led by Eugene Huang here that we have just passed the design review in October 2016. I would say that this progress wouldn't have happened without Fred's support and encouragement, and also sometimes very difficult questions from him. So actually, so the field of 21 centimeter has actually expanded very quickly. Now there is a few very large-scale dedicated surveys, instruments, telescope being built or has been built already, mostly Chime and Tianlai, and also Bingo and Hyrax. They are all scattered around the world and trying to go after the signal at redshift around 0.8 to 2.5. And also I wanted to mention that at the redshift around 10 or so, Fred has also helped the establishment or help the pushing the project called paper to measure the 21 centimeter signature from the epoch organization. And now paper has evolved very quickly, smoothly with the support from NIAO, and now is the next incarnation, which is called HERA, is now major NSF-funded instrument in the US, and now it's under construction. So I think the field actually owes Fred a lot of credit for where we are now. So basically, in summary, so I quickly talk about the amoeba, the CMB polarization field, and also the establishment of narrowgraph and the GPT, HIM, or even the 21 centimeter cosmology field that Fred has had a huge influential influence on, which we are really grateful for. Thank you.
So it is possible for you to review the whole field in half an hour. That's why I keep asking. So, questions?
Yeah, thank you for that tour de force. I didn't think you could do it, but you did do it.
Thank you.
I think, from an outsider's perspective, what you described about all we've learned from the fluctuations, what initiated them, what their character is, even gravitational waves. The most puzzling aspect is actually none of those. The most puzzling aspect about modern cosmology is the dark energy, okay? What is the prospect there in terms of learning? What is its character? Is it really just Einstein's cosmological constant, or does it vary with time? Is there some progress in sight on that problem?
Well, I think observationally now the approach is really just to measure the expansion rate of the universe to across redshift, trying to learn you can first answer whether that was a constant, or if not, how they evolve in time, and also whether this star energy model is viable or not is also an interesting debate. So people have been thinking about modified gravity. Maybe Einstein was not correct. So theoretically there were sort of two camps going after this phenomenon. But I think fundamentally on the theoretical side, there's no currently, as far as you know, there's no viable theoretical context for this yet. And I think the progress will have to come from all the longitudinal structure surveys that we talk about, trying to learn the behavior as a function of redshift, and maybe perhaps that will shed some light on the property of dark energy.
Another question? Well, I think it's impressive. The last few talks, all day, is how Fred imprints his will and vision. Not just here, not just at NREO, but sort of all over, right? In China, and it's just pushing on all fronts. So I wish our young people were here to observe this.
Right.
To imprint this style of